Hey everyone, and welcome. Today we're going to tackle a huge topic, gravity. We're going to go on a journey to really understand this invisible force that connects everything. From a simple apple falling from a tree right here on Earth to the silent, majestic dance of the moon way up in the night sky. So right off the bat, it sounds kind of crazy, right? A stone just plummets straight down. Bam, hits the ground. But the moon, it just circles us endlessly. It feels like a total paradox. But trust me, by the end of this, you're going to see how they are driven by the exact same beautiful, fundamental principle. All right, let's dive in. So first things first, let's start with what we all know and feel every single day of our lives, Earth's relentless downward pull. Now, this is one of those ideas that can really mess with your head at first. I mean, we've all seen a feather just kind of drift down slowly while a heavy stone just plummets, right? But here's the thing. That's only because of air resistance getting in the way. If you were to do that same experiment in a vacuum, that feather and that stone would fall perfectly side by side, accelerating at the exact same rate. So what is that rate? This right here. This is the magic number for gravity on our planet. We call it G. It's like the constant drumbeat that every single falling object marches to. Doesn't matter how big or small it is, as long as we can pretend the air isn't there for a second. Okay, so what does 9.8 meters per second squared actually mean in the real world? Well, it's pretty simple. It means for every single second an object is falling, its speed picks up by another 9.8 meters per second. So after 1 second, it's traveling at 9.8 meters per second. After 2 seconds, you got it, 19.6. It's this constant, totally predictable increase in speed, and it's all thanks to gravity. Now, this constant pull leads us to one of the most common mix-ups in all of physics. We throw around the words mass and weight like they're the same thing, but you know what? They are fundamentally different. Let's just break this down real quick. First, you've got mass. The easiest way to think about it is just the amount of stuff you're made of, all your atoms and molecules. And that amount is constant. Your mass is the same here on Earth, on the moon, or if you're just floating out in deep space. But weight is a whole different ballgame. It's the force of gravity pulling on all that stuff. So since the moon's gravity is way, way weaker than Earth's, you'd weigh a lot less there, even though the fundamental you hasn't changed one bit. I love this way of putting it. It really just perfectly captures the idea. Your mass is you. It's your non-negotiable physical substance. But your weight? That's the result of a conversation, a relationship really, between your substance and whatever gravitational field you happen to be standing in. Okay, so we've established that gravity pulls everything down, but clearly not everything goes down, right? And that brings us to the upward challenge, to the fascinating world of fluids. It's a fantastic question when you really think about it. You can drop a tiny little pebble in a pond and it sinks straight to the bottom. But then you see this giant, heavy log just bobbing on the surface. What is going on there? Well, it turns out gravity isn't the only force in the game. It's got an opponent. And here is our hero for this section, the buoyant force. It's pretty simple. Whenever an object enters a fluid, and that can be water or even the air, that fluid pushes back. It pushes upwards. This is the invisible force that lets massive ships float and giant hot air balloons rise. So how strong is this upward push? Well, the ancient Greek genius Archimedes figured this all out. When you put an object in a fluid, it has to shove some of that fluid out of the way, right? It displaces it. Well, the fluid creates that upward buoyant force in response. And here's the brilliant part. That upward push is exactly equal to the weight of the fluid that got pushed aside. It's this perfectly elegant balance. So really, it all just comes down to a simple tug of war. If that upward push from the buoyant force is stronger than the object's own downward weight, hey, it floats. But if the object's weight is just too much and it overpowers that upward push, it sinks. That simple battle is what decides whether a massive steel ship sails across the ocean or plunges to the seabed. All right, we've seen gravity pull things down, and we've seen fluids push them right back up. Now it's time to scale up our thinking. Let's take this whole principle and launch it into the vastness of space. And here we are. We're back to that huge question from the very beginning. We know for a fact that Earth's gravity is pulling on the moon, constantly, every second of every day. So, why doesn't it just come crashing down on us like a giant apple from a cosmic tree? This is the secret. It's a two-part motion. So yes, the moon is falling towards us. But at the same time, It's also moving sideways at a ridiculously high speed. We're talking about 1 kilometer per second. It is this incredible forward motion that changes absolutely everything.
So what's really happening is that gravity is acting as what physicists call a centripetal force. Think of it like a cosmic string or a tether. It's constantly pulling the satellite inward, preventing it from just flying off in a straight line out into deep space. Gravity is what bends its path into that continuous circle, or in most cases, an ellipse.
And this, right here, this is the beautiful aha moment. An orbit isn't about defying gravity, it's about using it perfectly. A satellite is constantly falling toward Earth, but it's also moving so incredibly fast sideways that the curve of its fall perfectly matches the curve of our planet. It is always perpetually falling, but it is also perpetually missing. That is what an orbit is. So there you have it. We've gone from a simple drop to a celestial dance. And it was all guided by the very same set of rules. It really makes you wonder, doesn't it? What other fundamental, invisible forces are out there, all around us, shaping our reality in ways we haven't even begun to understand? The universe is just full of them, waiting for us to figure them out.